Okay, good day. So let's have another discussion for a miscellaneous topic here in the analysis and design of flexural members. So this is a web crippling. So for web crippling, if the concentrated load is applied at a distance greater than or equal to the d over 2 from the end of the member, then so we can compute r sub n using this equation. So we have the reduction factor for LRFD as 0.75. Then factor of safety for ASD is 2.00. Then for the next condition, if the concentrated load is applied at a distance less than d over 2 from the end of the member, that is for a condition. So this is L sub B from our previous discussion. L sub B is the bearing length for the concentrated load. If L sub B divided by the depth of the section is less than or equal to 0.2, then this will be the value of R sub n using this equation. So the same factors. Then for the other case, if the bearing length divided by the depth of the member is greater than 0.2, then this will be our equation for the R sub n. And again, so we have the same factors. So basically, what is web crippling? So this is an example, okay? An example of web crippling. So we need to check if the section is adequate enough to prevent web crippling if it is carrying a concentrated load, okay? So let's have an example for analysis and design of flexural members, okay, by checking the web crippling. Okay, so let's have an example. Okay, so a W21/44 has been selected for the beam shown. Lateral bracing is provided for both flanges at beam ends and at concentrated loads. If the end bearing length is 90 millimeters and the concentrated load bearing lengths are each 75 millimeters, so check the beam for web crippling. Okay, so we have here again, so we have the same beam from our previous discussion, that is for the local web yielding. So again, first thing to do, we need to compute for the value of the reaction, so the ultimate value. So let's say this is the R sub U. So that is for the support reactions. So again, what is the value of our ultimate uniform load? That is the ultimate uniform load is equal to 1.2 of the uniform dead load plus 1.6 of the uniform live load. But for this example, we don't have a uniform live load. So let it be 0. So let us compute for the ultimate uniform load, that is equal to 1.2 of the given. So this is 15.24 kilonewtons per meter, including the beam weight. So this is multiplied by 15.24 kilonewton meter. And this is equal to, we have 1.2 plus 1.2 times the 15.24. This is equal to 18.288. So this is 18.288 kilonewtons per meter. For the value of the ultimate concentrated load, that is equal to 1.2 of the concentrated dead load plus the 1.6 of the concentrated live load. But for this example, again, so we don't have a concentrated dead load. So let us assume this value to be 0. So the value of the ultimate concentrated load P sub U will be simply equal to P sub U equal to 1.6 of the given. What is the given? P sub L is 155. This is 155.7. Okay, so again, 155.7 kilonewtons. And this value is equal to Okay, we have 1.6 multiplied by 155.7. That is equal to 249.12 kilonewtons. So again, we are now to focus on the computation of the support reaction. So that is for the ultimate value of the support reaction. So basically by mechanics, so instead of the W sub D or the uniform dead load, so we are to replace this one by ultimate uniform load. Then instead of the live loads, so we have two concentrated live loads, so we replace them with the value of P sub U. So by mechanics, so this is by summation up. Okay, so summation of forces vertical equal to 0, assuming upward forces to be positive. So we have 2R sub U minus, we have 2P sub U, and equivalent weight of the uniform ultimate load, that is the W sub U, or the ultimate uniform load, okay, multiplied by the length of the beam equal to 0. So if you are to compute for this reaction, okay, the R sub U is now equal to I. So if you are to transpose that value, it should be positive. So this is 2P sub U minus the uniform ultimate load times the length, or this should be plus since we are also to transpose that value, divided by 2. So we have the R sub U is equal to twice up. What is the value of our P sub U? That is equal to 249.12 kilonewtons plus our ultimate uniform load is equal to 18.288. And the total length of the beam as per given, okay, the total length is equal to 4.5 meters. So this is to be multiplied by 4.5 meters, then all over 2. So this is the value of the R sub U. Okay, 2 times this value plus, okay, we have the 18.288 multiplied by the length of the beam. This is equal to 4.5 meters. Then divided by 2. So our R sub U is equal to 290.268 kilonewtons. So let us check if we have a web crippling at supports. So again, at supports, okay, so this will be a support reaction, okay, acting within, okay, so our bearing length is equal to 90 millimeters. So what is our section or the wide flange to be used? That is W21 by 44. So we list down the properties of W21 by 44, and its total depth is equal to 526. So obviously, this R sub U is acting at a distance less than the D over 2 of our section. So if we are to go back on our reference, okay, so it will be on this condition. So the second one. So again, this is the first condition. This is the second one. If the concentrated load is applied at a distance less than D over 2 from the end of the member, then we need to check the ratio of the L sub B over the total depth of the section if it is less than or equal to 0.2. So at supports, so what is our bearing length? So bearing length is equal to 90 millimeters. So let us check the ratio. This is, we have the L sub B divided by the total depth of the section is 526 millimeters. Divided by D is equal to 90 divided by 526 is equal to, so we have that as 90 divided by 526. Okay, it is 0.17. So this is 0.17. It is less than 0.20. And the point of action, so RU is acting at less than at a distance, it is at a distance less than d over 2. So what is d over 2, by the way? So d over 2 is 526 divided by 2. So what is that value? Okay, 526 divided by 2 is equal to 200. This is equal to 263 millimeters. And okay, again, so this r sub u is acting within this bearing length of 90 mm from the left end. It is less than 263 millimeters. Is it 263? Yes. So therefore, okay, we'll be using this equation. The r sub n is equal to 0.40 of the t sub w squared. This close bracket, then multiplied by the square root of this value. So we have that equation. Okay, so this one. Okay, so this expression is applicable for the support reaction. So what we have to do now is substitute. Okay, we have this is the value of r sub n is equal to 0.40 of what is the thickness of the web. So for the W21 by 44, the thickness of the web is 8.89. This is equal to 8.89 squared, then multiplied by, we have 1 plus. This is equal to 3. L sub b is equal to 90. The total depth of the section is 526. Then the thickness of the web is again 8.89. Then the thickness of the flange, the properties of W21 by 44, the thickness of the flange is 11.4 mm. Okay, so divided by 11.4, raised to 1.5. Then close bracket. Okay, multiplied by the square root of E, this is equal to 200,000 megapascals for steel. Our Fy is given as 345 megapascals. Okay, so it's 345. Okay, then the thickness of the flange is again, this thickness equal to 11.4 millimeters. Okay, then to be divided by the thickness of the web, this is equal to 8.89. If we are to do unit analysis, so the unit of this, the resulting value will be in terms of the newtons. So we are to multiply this one by 1 kilonewton is to 1,000 newtons. Okay, for the final value of the r sub n to be in kilonewtons. So r sub n is equal to so I'll be starting on this term with the square root. So this is the square root of 200,000 multiplied by 345. Then the thickness of the flange is 11.4. Then to be divided by 8.89. Okay, then multiplied by 0.4 by 8.89 squared. Okay, then to be multiplied by the value within this bracket. That is 1 plus 3 times. We have 90. Okay, to be divided by 526. Okay, then to be multiplied by 8.89 divided by the thickness of the flange, which is equal to 11.4. And this is raised to 1.5. Okay, so again, this is in terms of newtons. So to be divided by 1,000 for the value to be in kilonewtons. So let's say the value of r sub n is 402. This is 402.48 kilonewtons. Then we need to compare the value, the factored value of r sub n. So this is we are to multiply P of r sub n, and it should be greater than the actual ultimate reaction. So basically, again, this is the capacity of the section, then the actual ultimate value of the support reaction. So we have P of R sub n. So what is our reduction factor for this one? So reduction factor is 0.75. So this is, we have we have 0.75 of 402.48. So is it greater than our RU? So what is the value of RU a while ago? That is equal to 290.268. So it should be greater than 290.268 kilonewton. So again, so the left side is the capacity, the right side is the actual value. So we have this is equal to 0.75. So what is 0.75 of this 402.48? So 0.75 of 402.48. And that is equal to 301.86. So 301.86 kilonewtons is greater than 290.268. So therefore, we can conclude again that W21 by 44 is adequate. Okay, when it comes to the web crippling at supports. Okay, so we satisfied this condition. That the P of R sub n, the capacity is greater than the actual concentrated load at supports. Okay, using this is under under LRFD method. Okay, so there will be we can conclude that there will be no web crippling at supports. Okay, so next is, let us check if there will be a web crippling under this concentrated, under these two concentrated loads. Okay, so we say at concentrated loads, so at concentrated loads, so which expression will be useful or applicable? Okay, so let's check again our reference. So that will be the first equation. So if the concentrated load is applied at a distance greater than or equal to the d over 2 from the end of the member, then we'll be using this equivalent of r sub n. Again, for LRFD, our reduction factor is equal to 0.75. So obviously, again, what is the depth of this section? For W21 by 44, the depth is equal to 526. If we are to consider its half, or that is the d over 2, it is obviously less than 1.5 meters. So we'll be using that expression or that equation. And that is this equation. Okay, for this one, so we'll be using this equation. So we are now to substitute. Okay, so this is for the R sub n at concentrated loads is equal to, we have 0.80 of, the thickness of the web. So what is the thickness of the web? We have that as, again, this is 8.89 squared. Then to be multiplied by 1 plus, this is 3 times. What is the length of the bearing length? The bearing length for concentrated loads is 75 millimeters. So multiplied by 75 mm is to, the depth of the beam is 526 millimeters. Then the thickness of the web is again 8.89 mm divided by the thickness of the flange is 11 point. Again, that is, I think, 11.4. We have that as 11.4. This is raised to 1.5. Then to be multiplied by the square root of E is equal to 200,000 megapascals for steel. We have Fy is equal to 345 megapascals. And the thickness of the flange is 11.4. To be divided by the thickness of the web is equal to 8.89. So we can now compute for the R sub n. So this is equal to, again, so I'll be starting with the term with the square root sign. This is the square root of 200,000. I multiplied by the Fy, 345 MPa. The thickness of the flange is 11.4. Then to be divided by 8.89. Okay, so this value to be multiplied by 0.8. Okay, 0.8 times the thickness of the web is equal to 8.89 squared. Then to be multiplied by, okay, we have 1 plus 3 times, okay, this is 75, divided by the depth of the section, 526. Okay, the ratio of the thickness of the web, 8.89, to the thickness of the flange, 11.4. Then this value is raised to 1.5. Okay, then this value again is in terms of the newtons. Okay, this is in terms of the newtons. So we are multiplying 1 kilonewton is to 1,000 newtons. So for this value of R sub n to be in the kilo newtons. Okay, so this value to be divided by 1,000. So we have that as 769.92. So 769.92 kilo newtons. Now we need to compare the value of this, the P of R sub n, the capacity, if it is greater than, the ultimate concentrated load, that is the P sub U. So this is our reduction factor for LRFD is 0.75 of 769.92 kilonewtons. Is it greater than our ultimate concentrated load? So the ultimate concentrated load, or the factored value, is equal to 249.12 kilonewtons. So is it greater than 249.12 kilonewtons? Okay, so let's have this value. What is 0.75 of this value? So multiplied by 0.75. It's 577.44. So this is 577.44 kilonewtons. Is obviously greater than 249.12 kilonewtons. So basically, we satisfied this condition that the capacity is greater than the ultimate value of the concentrated load. So we can now conclude, okay, that the W21 by 44 is adequate. Okay, since it is adequate, we can conclude that there will be no web crippling under each concentrated load on these points. So no web crippling for support reactions, and there will be no web crippling under the concentrated loads. Okay, so this will be our solution for this example. Okay, so the web crippling.